Hello everyone, and first of all, thank you for joining my talk. This is first time I am speaking in the bunker under these lights. That's kind of exciting, but I have done some preparations. We have a link to the slides. It is on the bottom of each slide, so no hurry to photo. It will be here. And I go under the same name on all the social networks, so if you want to contact me after the talk to ask some questions or just take a photo and tag on Twitter, you are welcome. Why this talk? After 20 years of software development, right now I am mostly doing research to provide a technical expertise for the company I'm working for. We at Evron create custom software, and it's very important for us to write readable code so our clients can handle and maintain software we created and can recommend our fine software craftsmanship. And you see, from our expertise, it's very hard to write readable code. And with this talk, I want to discuss origins, why it's so hard to write readable code and what we can do about it. Let me start with something unusual. With artists, painters who create their masterpieces stroke by stroke. They can always take a step back to see the bigger picture. And I can tell that we developers, we also create our source code stroke by stroke, identifier by identifier, operator by operator, expression by expression, but we cannot take a step back to see the bigger picture. We just lack the machinery of visual cortex that is useless for source code. For the source code, our memory is much more important, but our short-term or working memory is limited, and our long-term memory takes a really long time to put something in. This leads to the dread software complexity problem as depicted by my close friend Alexander Yereminy, a famous Russian comics artist, at least how we see it. But what's with other fields like, I don't know, engineers who create spaceships? We call them rocket scientists. Do they have the same complexity problem? Yes, they do, but they also have an education. Years and years of education. Wannabe rocket scientists, they start with kindergarten, where they learn basic calculus. They continue to school, they learn math, physics, and up to the college, where they learn all the things required to build the rocket. And after that, they have best practices accumulated by generations of people who create rockets, and practice makes perfect. So 15th rocket they create actually makes it through the atmosphere. But software development is different. We have zero copy cost. If we already written some code, we can copy it instantly. It costs nothing. So we always write new code. We always write code for new things. And our industry is young. We did not accumulate best practices yet. As a result, we have no software development education. We do have this strange thing called computer science, but it's mostly science and mathematics. It has really weak connections to actual software development. And we can't really learn by example. Artists, painters, they can. They can go to art gallery, look on their pictures and like, okay, this picture is really good, so I will try to paint it 100 times and will be an amazing artist. Artists and painters can do such thing because they have an intuition built into their brains. Our brains learn from our birth to categorize things, to learn which painting is good and which painting is bad. But this intuition, it operates on the real world. And if you try to apply it to the source code, answer it gives us will be that source code written by other people are always bad. We feel this intuition to throw it away and rewrite it from scratch. Our intuition simply doesn't work on the source code. We lack this built-in feeling which source code is good and which source code is bad. And it's really hard for us software developers to learn from masters. Painter, he can go to art gallery and he can see thousands of pictures instantly. We can go to GitHub and what? If we want to read the source code of Kubernetes, it will take months, if not years. And there is no intuitive way to us to distinguish between good Golang code within Kubernetes and bad Golang code within Kubernetes. Even more, for our clients, people who actually order source code and applications from us, there is no intuitive way to measure the quality of our source code. There is no intuitive way for them to handle things like architecture or tech debt. This leads to the complexity being accumulated in our industry much faster compared to other industries. And sometimes just in half a year, we throw out our software and rewrite it from scratch because complexity accumulation makes our code unreadable and unmaintainable. We can't remove the complexity from our source code. This complexity reflects features of our product, our backlog, our business needs, but we can redistribute this complexity, and my talk is mostly about complexity redistribution. And we have different options to redistribute the complexity within our Golang code. And the first option I want to talk about is our physical human memory. On the slide, this picture depicts the hippocampus within our brain that is supposedly to have something to do with our memory. Neurophysiology, I'm a hobby neurophysiologist, doesn't know exactly how hippocampus is connected to our memory, but if hippocampus is damaged, our memory is damaged. So it has to do something with it. And we know for many years that our short-term memory is limited. Miller's Peirce states that we can hold like 7 items in our short-term memory, give or take 2. But a recent neurophysiology research shows that this number is smaller. much smaller. Actually, it revolves around the 5 new items that we can hold in our short-term memory. And our long-term memory is unlimited. Our brain learned how to move things from short-term memory into long-term memory through repetition. And I really like to provide chess game as an example. New players to chess game, they really struggle. They look to the game board and they see lots and lots of chess pieces. They can hold only 5 chess pieces in their short-term memory. So they slowly scan this chessboard to understand what is happening. But experienced chess players who played thousands of hours, their brain learned patterns, moved them from short-term memory into long-term memory. Experienced player, they can look on the chessboard and they do not see individual pieces. They see high-level strategic things like aggression to the left and possibility of 2 different attacks to the right. And actually, we, software developers, can use same trick with libraries and framework. If some software developer uses library or framework months and years, their brain automatically learns patterns, move them from short-term memory into long-term memory. And after some experience, developer doesn't use any cognitive power to comprehend the source code. They can see only new things. This leads us to the first controversial thing, that actually sometimes in order to write readable code, we don't need to pick a best library or framework, most suited tool for our job. No, we can just pick the library or framework that is most popular. So many developers already have experience with it and patterns are within their long-term memory. Same with coding standard within our team. From neurophysiology point of view, it's not here to make our code pretty. It's here so patterns within our memory moves from short-term into long-term memory, and after some months and years of using same code style, developer doesn't use any brain power to comprehend it. They can ignore most of the code on the screen and just focus on 2 new items that are important, really reducing the complexity of the source code, making it more readable for them, because they have this information into their long-term memory. And Go provides out of the box a great Go format and Go link tools, and I personally think that it's one of the strengths of the Go programming language, because it forces some syntax, it forces some style, and this allows most of Golang developers to have same information into our long-term memory, and our code that we write is readable to each other. Of course, sometimes this backfires. For example, if a developer comes to the Go programming language from, I don't know, JavaScript or C++ as me, some patterns can be unusual. Yes, I am perfectly aware that Go uses automatic semicolon insertion, so we just can't handle the else style as it is for other languages. But you see a little rant. A few months ago, I interviewed Yukihiro Matsumoto, an author of the Ruby programming language, on the big Ruby conference in Moscow, Russia. And he told me that Ruby core development team, they put great effort into making language easier for developers, despite the fact that it requires them to work really hard to make the code of this language. It's hard for them to create language, but easy for developers to use it. I hope that during the Go language evolution, we will have some improvements into common patterns. But okay. Moving things from short-term into long-term memory takes time, but we want to write readable code right here and now. What other options do we have? We have classical decomposition. If more than 5 things accumulate into single place, we can decompose it into piles of 5. And if we observe an evolution of typical software, typical Golang microservice, it starts with a single file, and after that, number of files increases alongside the software complexity. As more things grouped together, more than 5, we decompose them into packages and into language abstracts like structs, interface, channels. We write code, and lots of things are still packed together, increasing its complexity. So we provide some external domain-specific languages, like put some configuration into JSON, XML, YAML, and as the pinnacle of decomposition, we break our software into individual software. It's what we are doing right now with Golang. We decompose our software into hundreds of microservices. I do not know the answer to the question, what will we do if we have a few thousands of these microservices? But that's the question for another talk. Libs, libraries, and decomposition, they are good, but definitely not enough to remove all the complexity that is contained in tens of thousands, hundreds of thousands lines of source code they produce during the typical software creation. And have other options to fight with complexity to redistribute it. We can redistribute the complexity into meta information, road signs that are not for language itself, but for us software developers. Road signs are, for example, identifiers. There are tricks with identifiers, and I'm quite happy that I'm giving this talk in Germany, because I always provide an example as a German word. German language, yes, it's famous for gluing words together into very long words, and this word is a perfect example of how our short-term memory operates. Actually, this word takes only one slot in our short-term memory, and we can put additional information into identifiers without a fear that these identifiers will blow up and make our code unreadable. No, they are pretty fine. And fine identifier, it answers the what is it question. We use mixed case to glue words together. And what I really like about Go language is that our documentation, manual, it explicitly says that identifier length should increase alongside the complexity. If we write really simple code, we can use identifiers like I, G, V, but if we put more things, items into this part of the code and complexity grows, we just increase the length of our identifiers so they offload some complexity into themselves. We can put road signs into comments. A good comment, it answers the for what purpose question. Because code itself, it answers the questions like what is it? We are developers, we can read it. But the purpose of this code is additional complexity that is not always obvious from this code. And good comments actually answers it. I can show. The easiest place for comments inside our source code. And if you want a good comment that answers the for what purpose question, we can do it pretty easily if we focus on these questions. Comments, they are not limited to our source code. We can put these road signs into commit messages if we use blame system and can always see these messages for each line within our IDE. And we can even put additional information, redistribute the complexity into our tickets if we link our commits with tickets. Last place within our project to redistribute the complexity is our documentation. I really do not like to redistribute the complexity into documentation because it's very easy for documentation to go out of sync from our source code. And yes, documentation can be auto-generated, but it's not always the case. Not all the software we create are simple API services where all complexity goes into API documentation. No, business come alongside business logic come, and we cannot generate documentation from business logic, but we can redistribute some complexity into it. And sometimes even into test, because test, it can not only test our software, it can actually double as documentation and demonstrate some execution paths within our source code. Yes, test can make our code more readable. And last thing we have to redistribute the complexity is types. Unfortunately, types, they can be used as additional means in dynamic programming languages, but Golang is not dynamic. So I included types only for their consistency. There is a saying that false consistency is the hobgoblin of little mind, and I really like the hobgoblin beer. There is no gradual typing in Go like in Python or JavaScript or Ruby, but we can use the gradual approach that revolves around 5 to make our code more readable. Gradual approach starts with gradual decomposition. If we see lots of new items within our code, we decompose our code into different things, into files, structs, interfaces, external configuration files, microservices, and so on. As complexity increase, we decompose into road signs, into meta information. We put additional meta information into our identifiers, into our functions, into our names, so making our code more readable. And for languages with gradual typing, we can use types as additional means. With Go, we always use types. It is good, it is bad, but it's what we have. And as the number of new items in our source code increase, we use one of the options provided to the left to redistribute this complexity and make our code more readable, if I want to put all of this into one sentence. And what is new item? It actually depends on the content of our long-term memory. And you see the tricky thing is different developers with different background, with different experience, we all have different content of our long-term memory. And given the same source code, we will see different things as new. We will redistribute the complexity different ways. And this leads to really strange things like, for example, why it is bad to have a team of software developers of equal level with one superstar. Because this one superstar, they have lots and lots of patterns in their long-term memory. They will write code and they will redistribute the complexity basing on their knowledge. And the rest of the team, they will look on this code and this code will be unreadable for them because it was redistributed by completely different rules. So it's really important for our teams of developers to have same background, to use same libraries and base our writing on same coding standard and use these options to redistribute the complexity, of course. Writing readable code is a tricky thing. There is no silver bullet, and this gradual approach I just highlighted, it can't be applied to all situations. Sometimes we do business automation with fixed waterfall design. Sometimes we do drivers that are completely different, and I just scratched the surface actually because a readable code is not only how it is written, it's also algorithms, architecture, lots and lots of things. But I think if we have a team of developers and we want to improve the readability of our source code, we can always start with the rule of 5 and the gradual approach of redistributing the complexity. And that's the thing I want to discuss with you today. Thank you. And we have 5 minutes for our questions, please. And remember that I am just a hobby neurophysiologist and I do not have a medical education, so I can talk a lot about our brain internal wiring, but take it with a grain of salt, please. Microphone, please.
Yes. Is this on? Yes.
Yep.
When you were speaking about types consistency, you mentioned some examples. I just noted down goblin. Can you elaborate on that, please?
Types consistency, types consistency, types consistency. That's tricky question because I do not remember talking about type consistency. Do you mean the types as a way to redistribute the complexity into?
Yes, it was in this part.
Yeah. That's a good question. I skipped a bit. You see, in dynamic question, in dynamic programming languages, I'm not only C++, I'm also Python, JavaScript, Ruby. They all provide this gradual typing thing. So if we write simple code in our dynamic language, we just skip types because it is the good flow of our execution, and if something bad happens, we can always explode with exception, crash, and fix our bugs. But as complexity grows and we want to add some error control, some corner case check, we gradually introduce types. And if a developer for the dynamic language, they see types, they know that these types, they are mark road signs, that this code has something complex within, and they need to think accordingly. That is the gradual approach to using types. Of course, Python can be used with like 100 types. Always use types. This way, Python can be used just as the Go programming language. But it is not the best usage for the dynamic language alongside the gradual typing. More questions, please? We will also have a coffee break afterwards, so feel free to catch me there. That's all. Okay.